So welcome, everybody. Thank you so much for coming. Today we're really lucky to have Thordarson come talk to us, a man that Stephen Colbert calls a man so nice they Thored him twice. So he's got that little moment of fame there on the Stephen Colbert show. But I was trying to think of what to say about Thor, and so I thought about manifest destiny. Because if you're born on an island in the middle of the ocean that's both a hot spot and a divergent plate margin, you may become a volcanologist. If the first time you see an eruption is when you're 6 years old, it happens to be the Surtsey eruption of 1964, you might become a volcanologist. If you walk on an active lava flow at the age 15, you might become a volcanologist. If you get your college degrees from the University of Iceland and the University of Hawaii, you're probably going to become a volcanologist. And if you are lucky enough to work with and be mentored by some of the most well-known and renowned volcanologists in the world, you might become one yourself. So Thor has, I would say he almost had to become a volcanologist, although he'll come up with all these reasons why the path might have changed. But he's had a very interesting path. He's worked on volcanoes all over the world, everything from the Ruapehu volcano in New Zealand to incredibly old lava flows, 3 billion year old lava flows in Australia, which is where I met him. Worked in Scotland. And eventually was able to make it back to his beloved Iceland, where he's the professor of volcanology and petrology at the University of Iceland. So today he's here to answer all your questions, everything you ever wanted to know about volcanoes. No pressure. But I give you Thordarson.
Yeah. Hopefully this works, the microphone. Yeah. Well, when I was 15 and I was walking on that moving lava in Heimaey, I had no idea what the volcanology was even. So I had not made up my mind about my career at that time. It came a bit later on. But anyway, what I wanted to do is talk a little bit about what's going on in Iceland at the moment. And this is, of course, a work that involves many people. And there's actually a bit of history behind all that. We've got 2 European research projects which actually helped us to develop methodology to assess and evaluate volcanic risk on volcanic islands. So it came in handy. We did this from sort of 2014 and until about 2021. But so we had all the tools ready when the eruptions started in the Reykjanes Peninsula in southwest Iceland. And it's kind of a funny, in 2019, this TV reporter in Iceland approached us and said, I want to do a show on the volcanic risk in the Reykjanes Peninsula. And so we did. And we went out there and told our story and basically sort of highlighted the things that we thought were risky on the peninsula and that it will erupt sooner rather than later. And then 1 year later, it actually started to erupt. And they reran the show that year just to remind people that what had been told the year before. Because really, when we said this originally, a lot of people got upset and said, why are you trying to ruin the property prices in the Reykjanes Peninsula? No, that's fine. So anyway, a lot of people and a number of names here. I'm probably missing someone. And from a lot of different countries, a lot of European countries, even from Indonesia, United States, Canada, and Mexico. Now, what is Iceland? This is a big hunk of rock in the middle of the North Atlantic. And if you take the shelf area around Iceland, along with what you see above sea level, it actually is about I'm used to say this in kilometers, so I'm going to do that. That's about 800 kilometers across. Now you can translate that into miles.
We're all scientists, we can measure.
That's good. And but what we have here is an area which covers about 400,000 square kilometers. So it's about the size of Washington State. And it actually is a mountain plateau that rises more than 4,000 meters above the surrounding seafloor. So if you were standing south of Iceland, you would see these massive mountains right in front of you. And it's all produced by volcanism. So these are just eruption after eruption, probably on the order of anywhere between 5 and 10 million eruptions since Iceland started its activity, producing lava flows that pile on top of each other, and in the end they build up this massive oceanic plateau, so to speak. And the reason why Iceland is here is because it so happens that we have underneath Iceland a mantle anomaly which is lighter than its surrounding, and it's actually rising up. Some people refer to that as a mantle plume, sitting right on top of mid-ocean ridge segment where plates are moving in the opposite direction. This is the American plate here, or the North American plate here, going to the west, and the Eurasian plate here going to the east, as you will see later on. And because of this superposition, we have unusual volume of volcanism or magma produced in this region, and that basically is the reason why Iceland is above sea level, and that's why we call it a hotspot. Because it has an unusual amount of volcanic activity. I don't need to put, and for comparison, so the volume of Iceland is 2 to 8 billion cubic kilometers, which is about the size of the largest flood-coastal provinces that we know on Earth, like Deccan Traps and Siberian Traps. To give you some idea, if any one of you know the Tesla Gigafactory in Texas, this is how many of them you need to cover Iceland. Now, a little bit about sort of the geology. Compared to the geological map that you look at, for Michigan, this is actually fairly straightforward and simple. The oldest rocks are on either end of the island, and the young rocks are in the middle. And so here is the active spreading axis, and this is sort of a segment that is new and newly formed, and is in its growth period, called the Eastern Volcanic Zone. But we have all these names: the Reykjanes Volcanic Belt, Western Volcanic Zone, Mid-Iceland Belt, Northern Volcanic Zone. But it's all basically the same structure. It's the suture between those two plates which are moving in the opposite directions. Like I said earlier, North American plate and the Eurasian plate. So I'm not going to bother with, but also Iceland is very young. And so the oldest rocks you see at the surface in Iceland are about 16 to 18 million years old. Now, when I was working in Australia, we would do the age dating. The plus or minus sign on the age date was plus or minus 50 million years. So Iceland is only half of that. But so quite young structure. And like I said, the plates are moving opposite direction, 1 centimeter per year. This is what we call the Reykjanes Ridge, which is part of the mid-Atlantic ridge system, comes up to Iceland, and it sort of punctuates and sort of ends here in southwestern Iceland. There's another segment that comes from the north called the Kolbeinsey Ridge, and it comes in here and sort of in northern Iceland. And the plume sits right at the sort of the suture between these two, and is the reason why for the complications, especially in the structure, the tectonic structures of Iceland. This is where the ridge comes ashore in southwest Iceland. So this point is down there. You can see the fault, normal faults here, the southern escarpment, but it's not as well defined on the north side. But this is basically where this ridge is coming ashore. This is the start of the Reykjanes Peninsula, and start of the volcanic zone, which is there. This image here, this is a GPS-based image where basically mapping out relative movements. So this red here is the movement in millimeters to the east, and the blue is the movement in millimeters to the west. And you can see sort of as it is today, this seems to be where the plate boundary is located in Iceland. If you go to the previous slide, you see we have this drawn like this, but it seems like it's actually going more like this at present day. And the volcanic activity is not confined to Iceland, as the Reykjanes ridge approaches Iceland. So this is the Reykjanes Peninsula here. This is the image that I showed you where the ridge is coming ashore. But offshore we have a chain of volcanoes that have erupted quite frequently in recent times. This is just covering the last sort of 800 years or so. And this is the only things we know of. There's probably many more eruptions that happened, which we never even noticed. But this is a sort of submarine eruptions. They build sometimes island that actually will rise out of the sea. There is one up here called Eldey, which is the biggest garnet nesting area in Europe. But it was formed in an eruption, sorry, it's over here, 1926, not 26, in 1200, around 1240. And, but 1783, an island formed over here, further south, and as the Danish merchants were sailing towards Iceland in the spring of 1783, they noticed this eruption and this new island. So they were quick to send a message to the Danish king, said, there's a new island forming in your kingdom. And the Danish king sent out his warship with his flag. He was going to claim that island before anyone else could. And by the time they got there, the island was gone. The ocean had actually basically eaten it up. So no claims of land there. I just put this in for fun. This is on 8th of February this year. Eruption started early in the morning. This happens to be my sister's birthday. And a few days before, I was asked by a reporter, so when is the next eruption going to be? And of course, I don't know. So I said, it's going to be 7:37 on 8th of February. And it started at 7:40 on 8th of February. So I'm in trouble anyway. But it's a nice satellite image of Iceland showing, see, this here is actually the shadow of the plume which is here. And the eruption site is right there. Just a nice image. But a little bit about geology of the Reykjanes Peninsula, not too much. If we start with the tectonics, there's a lot of faults and fractures on the peninsula, and I'm not going to get into that in detail, but a lot of them are actually extensional fractures and normal faults. So because of the spreading, but you can sort of roughly see them group sort of into three main sort of clusters. And some people would argue that sort of is defining a system of some sort, whether you want to call it a volcano-tectonic system or just a tectonic system on its own right. But there's a lot of them anyway. So evidence of quite a bit of tectonic activity. This is a simplified geological map of the area, and the green blobs here are sort of the oldest volcanic rocks formed by the Reykjanes volcanic belt since the glaciers retreated. So we have older rocks which are formed in subglacial eruptions, which are sort of in along the central crest of the peninsula. All this gray stuff, that's much older stuff. So about 500,000 years old to a few million years old. But you can see these, quite extensive, these green blobs. So they cover a lot of area, and they are sort of the basement for the Reykjanes Peninsula as we know it today. And for example, this eruption here connected this part, which was an island, to the mainland about 14,000 years ago. So it's kind of the main building block of the peninsula, if you like. And then we have younger eruptions, which are shown here in sort of violet to purple colors. And those are all lava flows formed by effusive eruption that took place on a linear vent system. These here are all on a central vent, and we call them lava shields. Because when you look at them, they look like a shield that you've been basically dropped on the ground. And, but they actually range quite a bit in age, but these fissure eruptions, they're typically somewhat younger, even though there's a significant overlap in terms of their ages. And you can see that gradually these fissure-fed lava flows are sort of covering up the lava shields. And this is a very complicated geological map, the same geological map with some volcano-tectonic features on, which I'm not going to go into detail on in here because we'll see it better on the next slide. But basically what you see, that broken line here, that is actually outlining the area where volcanic activity takes place on the Reykjanes Peninsula. So this is what we would call the volcanic belt of the Reykjanes Peninsula. Outside of it, there is no volcanic activity at all. Even though the lava flows, because they flow, can extend beyond the areas where the vents are. And as such, it's kind of interesting to look at is that the red ones here, these are what I call lineaments. And these lineaments are defined by cone rows. So you see actually cones which sit on a volcanic fissure, and they form a linear structure. But they're not formed in a single eruption. They're actually formed by repeated eruptions on those lineaments. And these red ones are the ones which were active between the period of time from 800 AD to about 1250 AD, which we define as the last eruption period on the Reykjanes Peninsula. I'll explain that a little bit later. The yellow ones are ones which were active before that, but in the period basically from roughly about 2,000 years ago to about 14,000 years ago. So these are, but you see how narrow they are, and the vent systems are really, where the eruptions take place, are confined to very narrow linear structures, which is a reflection on why we have volcanic activity in the Reykjanes Peninsula and the tectonic forces at play. So try to explain that a bit. So the Reykjanes Ridge is coming ashore here. And then we have the western volcanic zone continue up here, and then this area here, which is linking the Reykjanes Ridge to the western volcanic zone. And in this, the area outlined here in red is also areas where you have the main volcanic activity taking place in recent times. And what happens is that we have, on the Reykjanes Peninsula, we have this period of time where sort of 800 to 1,000 year long periods where there's no volcanic eruptions at all. And then we get periods which last for 300 to 400 years where we have lots of volcanic eruptions. So they happen in these periods. And best way to explain that is because this plate is moving 1 centimeter per year to the west, and this one over here is moving 1 centimeter per year to the east. And in order to create a situation where you can have eruption, you need to have openings or stress release in this region here. So what happens over a period of 800 years is that you just keep stretching. You move this, and you can see the boundary. Sorry, I should point out, plate boundary lies across like that. So it is at a fairly low angle to the movement of the plate. It's almost parallel to it, not quite. So you're stretching that plate boundary, and you do that for 800 years. So you stretch it up to roughly about 16 meters. And it's just like if you have an elastic tape. You just stretch it, keep stretching it, and get to a point where you stretch it so much that it's going to break. And when it breaks, it snaps. That's what happens here. And it takes about 300 to 400 years to relax all that strain that you've accumulated over a period of 800 years. And that's when you have all these volcanic eruptions. The periodic unrest that we have during these eruptive periods, so there's not a continuous eruption, there you have distinctive events which are spread out across the peninsula at different times. They can last for a few months up to tens of years. And you have earthquakes activity, seismic activity associated with it. You have fault formation and extension. But each of these events, which happens on the lineament, they release roughly about the equivalent of 2 meters of stress buildup. So you need to get rid of the 16 meters that have accumulated in the period when you had no volcanic eruption. You need about 8 events. And when we start to count the number of unrest events, which we refer to as fires, on these eruption periods, here is one, this is the last eruption period, we have roughly about 7 to 10 events in each of these eruption periods. And then we have no eruptions in between. So it sort of roughly fits. And we have been able to map out 3 eruption periods in the last 4,000 years. Now the 4th one has started, which is the activity that we are actually realizing today. And the first 2 events of that have already taken place. And it so happens that collectively, they're actually very close to each other. They're basically in this area here. Collectively, they released about 2 meters of, equivalent of stress of 2 meters of stretching. You kind of like to put this in just to demonstrate that we do have a period of volcanic unrest on the Reykjanes Peninsula. Here's 2018 earthquakes of magnitude greater than 4, not that many. And now if you look at 21, 22, 23, you can see how that numbers has increased significantly. So this activity that we've seen on Reykjanes Peninsula has happened on a lineament. One is a Fagradalsfjall lineament. Features 3 short segments, one over here, one in here, and another one right there, that produce 3 lava flow fields in 3 eruptions. And we refer to these as the Fagradalsfjall fires. So it's all on one single volcanic lineament, but it's actually produced by 3 different eruptions. And then activity in 23, without any indication, there was nothing really that told us it's going to happen, because we've had all kinds of signals over here in the years before, like even starting in 2020, and nothing happened. But in 23, activity jumped over here onto the Sundhnúkur volcanic lineament, and there's been 7 events and 6 eruptions on that lineament in less than 1 year. And this is the collective lava flow field produced by those eruptions. So this is a product of 6 effusive lava or lava-producing eruptions, if you like. And this whole thing did not start without precursors. We had actually some precursors as early as 2019, late 2019 in December. And throughout 2020, there were seismic swarms, not necessarily in this region, but in the adjacent regions, but in the in February, early February, we started to see some increased seismic activity focused on this particularly this lineament here, the Thordarson lineament. And 24th of February, it really took off. And there were some really big earthquakes. We had magnitude 5 earthquakes associated with this early unrest, clearly related to magma trying to force its way through the lower part of the crust and sort of and up into the upper part of the crust and creating space for itself. But combination of movement of the plates, this 1 centimeter, and the relaxation of the stress that had built up because of that movement, and magma injection that is creating all this seismic activity. We haven't seen a swarm that big since. So this is by far the biggest seismic swarm that we've seen, lasted for 3 weeks. And on 19th of March, it actually resulted in an eruption. I don't know how you have sort of, whether you followed eruptions around the globe, but usually eruptions start with kind of interesting and magnificent display. Usually the intensity is the greatest in the beginning and then it tapers off. This eruption started out just by leaking out. There was not an intense thing. It started on 10 very small vents with a little bit of fire fountaining, and we caught it all by our drone videos. And it was such a low intensity that I was just staring at it going like, I don't believe this actually came up, because it didn't seem to have enough pressure to actually create that kind of a thing, but it did. And it was kind of an interesting. It actually, later on, did the reverse. It actually increased its productivity or intensity. So, but anyway, so to make, not dwell too long on these things, these 3 eruptions, Litli Hrútur, Meradalir, and Geldingadalir, all of these names relate to farming animals. So Geldingadalir is the valley of the geldings. So, and whether they are horses or bulls or rams, we don't know. Meradalir is the valleys of the female horse, the mare, and Litli Hrútur is the small ram. Kind of an interesting names for that. They're all fairly small eruptions. See the volume, 0.01 cubic kilometers up to 0.1. Only a few square kilometers covered by these eruptions. And the discharge or the intensity of these eruptions is pretty low, just a few cubic meters per second. In order to keep a vent or a conduit open through the crust so magma can come up to the surface in an eruption, theoretically the value is 3 cubic meters per second. That gives you sort of comparison. This is barely above that. So one wonders, why on earth did it come up? I don't have any answers for that. Anyway, so here is the first one. This is how the activity was in the afternoon on the first day. And you can see people here for scale. That's the tourist already arriving. And so it began quietly, but later on, it actually became quite intense. And this is the capital, Reykjavik, in the foreground. This is the main cathedral in Reykjavik, 75 meters high in total. And here is the eruption site behind it, with lava fountains, which at that time reached well over 200 meters. Here, you can't even see it. It's so weak. This is actually sort of in the middle of the eruption, so it actually increased in intensity. And the interesting thing about this eruption, it actually showed the whole range of activity that we know from basaltic lava-producing eruptions, including all of the lava types that we know have to be formed in a subaerial lava-producing eruption. And all from that sort of a very moderate kind of a quiet tourist-like eruption. Kind of interesting. Second one, oops, go back. Opened up on a short fissure about 300 meters long fissure, just a little bit further to the north. The interesting thing about that eruption really is that this pond here, well, one of the interesting things about it. And this pond was formed very early. This is actually a photograph taken about 4 hours after the eruption started. It already had formed a pond which was about anywhere between 6 and 8 meters deep. This pond stayed at this size for the remainder of the eruption, but on the 8th day of the eruption, it was actually 40 meters deep. And it just built up the walls on the margins of what's keeping the pond. It just kept growing up and up and up. And these overflows that you see here coming out of the pond, they built up also on the outside of those walls. So the actual walls that you could see, they were all never more than 3 meters above the lava surface on the outside, even though they were actually, the depth of the pond was 40 meters. So it was very interesting to see how this kind of a balance was maintained during the eruption. And then we had Little Hrútur, which formed quite a nice lava river that fed this, what we call Rupli Pahoe lavas and lavas further downstream. One of the main things about this eruption is that it actually produced quite a bit of vegetation fires, which was really difficult to extinguish. And so large areas around the eruption site burnt away, and it caused actually quite a severe pollution in the greater Reykjavik area. Sundhnúkar fires, really quickly, just show some, you've seen this map before. This is to date, the total amount of lava produced by these fires. This is the eruption on 14th of January. And you can see it actually, the fissure here, the berms that we raised around the town of Grindavik, which is here. This is the Grindavik harbor. This is a very important fishing town in Iceland. This is quite an important port as well, for the fact that it takes you only 30 minutes to get to the fishing grounds. So it's a cheap way of catching the fish and also a safe way to do it. So in order to try to protect the town, we raised protective walls or berms around the town. This eruption actually erupted through one of them, produced lava flow on the inside as well as on the outside of the berm, and that lava down on the inside flowed through a fissure down to this area right here, came up again as a new lava flow, and went over 3 houses in the town and burnt them. So that was a kind of dramatic scene for many people. But the onset of activity there started with very intense seismic activity. So this is recorded seismic activity between 25th of October to 17th of November, but centered on 10th of November, which is the main day when most of this happened. So these earthquakes formed, that comes down here, that's all happening on the 10th. And these lines here show actually the normal faults that moved in the event on the 10th of November. And so you can see the teeth here are pointing towards the side that dropped down. And so this is pointing in here and there. So this whole area here dropped down. And then we have another one, a narrower one on this side over here. And as you will see later on, the maximum drop here is about 1.5 meters. So if you had a house there, actually when you came back to it after this day, it was 1.5 meters lower than it had been before. And this is just kind of the same. This is showing the drop associated with this event. So it's an extensional event. Basically, you're moving the area here to the west and moving the area here to the east. Oops, keep doing that. But you can also see here, that is the color here, shows how much is dropped down. And so there's a major graben structure in here and going through the town of Grindavik. Oh, interestingly, this area here has also been uplifted on the outside. These are just photographs of some of the faults in town. This is the main road in Grindavik. That's what it looked like after 10th of November. And I was in Sweden at the time when this happened, but I'd been arguing that they should actually evacuate Grindavik some days before. And even on the morning of the 10th, I said, you should be evacuating Grindavik because there's so much seismic activity. And it hadn't even reached its peak. It reached peak in about 4 o'clock in the afternoon on the 10th. And with the really big earthquakes in that period, especially 3 really big ones. And there were still a lot of people in town. They did not even order the evacuation until 11 o'clock at night. And a lot of people got really, really scared because these earthquakes were right under your foot. Their origin was not somewhere else. It was underfoot. And some people actually said it was suspended in the worst events because the earth dropped from underneath them. So that's kind of a... And the Met Office people, they argued that this was all caused by some dike that came from unspecified source area and that moved laterally for 15 kilometers in either direction, underneath Grindavik and beyond Grindavik. So, and they claim that this seismic activity is generated by the emplacement of this dike. We don't have any evidence of that dike emplacement at all. And if it was a dike, it would be very strange. If you go to the southern end here, you can see the earthquakes get deeper. So they're of greater depth. And if the magma is generating that, that means that the magma is actually flowing down back into the crust instead of coming up. That does not make a lot of sense. Anyway, a colleague from the Czech Republic, they have also been analyzing the earthquakes, and one thing that they noticed, I want to go back to that. So why doesn't it do that? Nope. Doesn't allow me to do that again. And you can see that there is a seismic shadow there, and they argue that that's a magma accumulation zone. And this is 10 to 11th of November, and then here is the 11th to 18th when that is actually forming. Then we had an eruption on the 18th of December. And I think they actually got it right. Anyway, to just show you some images from this eruption. This is the first eruption on 18th of December, and the lava, you see the fissure is opening up. Just north of town, there is Grindavik, and the fissure, and some fissure segments here. This area here is actually where almost all of the eruptions have started, except for the one on the 14th of January. And this is just very close to what we call Sundhnúkur, hence the name. And this is the 14th of January eruption. Here you can see the protective wall that was raised and the fissure actually going through it. And here is the protective wall again, and the lava that is coming from vents that are on the south side or town side of the wall, they're actually going towards Grindavik, while all of the lava that's produced by the vents on the north side are going along the wall. So actually the protective wall did its job, even though it was breached. And as I was told earlier, there was a lava that came up through a fissure in this region here and flowed over 3 houses. Third eruption, 8th of February. That one actually produced a lava flow that was channelized very quickly and actually produced this reasonably long flow here. It was interesting that when it came to this point, part of it went this way and part of it went north. But land here is slightly higher elevation than the land here. So it was struggling to get this way, and that diverted all of the flow in this direction. So it moved very fast at one point over the road to Grindavik and in the direction of the Blue Lagoon. I assume some of you have heard about that major tourist attraction in Iceland. And there you can see the walls that are protecting the Blue Lagoon as well as the geothermal power plant, which is in that area. And here is the one on 16th of March. Now, because I'm not remembering what I wanted to say, take a notice also how short these eruptions are. And then we get to the fourth one, and certainly we got totally different scenario. An eruption that lasted for 1.5 months. And so kind of different. And these eruptions actually were more intense than previous eruptions in the beginning, and then quickly sort of dropped down to low intensity event with activity on localized segments of the fissure or single vents that maintained activity for most of the eruption. And this pattern has maintained since then, so this is just numbers on the volume of the fourth eruption, the March to April eruption, and this is the lava flow field as we know it, and the thickness of it. See, the discharge very high in the beginning, but it shouldn't say now, they should say late stage eruption. So it's kind of towards the end of the eruption, it's down by 3 cubic meters per second. Fifth one, very similar to the March one, quite a long eruption, high intensity to begin with, opened up on the same vents as previous ones, and breached some of the berms, and they were actually battling those things. As the eruption was going, they had both water cooled, tried to spray it with water to cool it down, and also basically building new berms on the inside to protect the power plant and the Blue Lagoon. The interesting thing is that this one here was actually started by man. One of the guys decided to have his digger to go in this area and use the rubble on top of the lava flow to load on top of the berm, but all he did is he opened a pathway for the magma to break out and flow over the. So there were mistakes made. And then this one is the last one, 20th of August to 6th of September, not as long as the previous one, but very intense. And what that one did, so most of the eruptions, they start, and all, including this one, they started down here. In all of the previous eruptions, the activity migrated and settled roughly about there. And that's where the long lasting activity in each eruption was located, was down here. But in this one, it started here, it started to migrate this direction, then suddenly it shifted and went to the north and settled on the vents over here, which are closer to the Reykjanes, the road to the airport. And it was kind of threatened the road to the airport. And people could actually, as they were driving from the airport to Reykjavik, they would actually see the volcanic eruptions kind of next to them. And it also went over the Grindavik Road and closed off the access to Blue Lagoon, so they had to close temporarily. Notice, Blue Lagoon has remained open for most of it. It's only been closed for a few days, maybe cumulative closure of 2 weeks, even though there's eruption next door. And this is sort of so here is the Keflavik, the road to the airport, the Keflavik Road, or Reykjanes, I don't know what to call it, but anyway. This is the lava as it was on the 28th of August to 4th of September, and is how it was migrating, and basically that's equivalent to about 1 kilometer in 6 days. So it would have taken it, if they would have continued, it would have taken about a month to reach the road. But if it goes over the road, then all access to Keflavik Airport is cut off. So it's a major issue because Keflavik Airport is the only international airport in Iceland. That's where all the air traffic goes from in and out of Iceland. So this was quite a bit of a concern. And lava's a funny thing. Sometimes they just move slowly, you can hardly see them move. But often in the beginning, when you have intense fire fountaining, then they can move pretty fast. And in this case here, there it's moving about 0.7 meters per second. So it kind of are going about a half a kilometer every 10 minutes. So it's a reasonably fast-moving thing. And also, way lavas flow, you don't often notice it is moving, even though it is moving. And as you will see in this time-lapse video here, this is actually from the 21 eruption. This little embayment here called Nátthagi will fill in with lava. And these people are not running, they're just walking. But you can see it as it moves in here and how it spreads quickly, but you don't see any red glowing lava. You see occasionally along the margins, you see red glowing lava, but you can see it continues to thicken. And it continues to thicken. And it's still thickening. And this is the most typical way lava is emplaced. And the key element here is that this crust that forms on top of it actually insulates the interior so it doesn't cool very much. And this makes it ideal for long lava flows to form. So it's a key to formation of long lava flows. And we can sort of do this again, I guess. And this inflation also is quite important because you see that it's a pretty thin sheet as it's coming in, but then it starts to thicken. And it can actually increase its thickness 5 to 10 times during this process. So just by this thickening, it can actually overcome obstacles fairly easily. And then continue its advance. Fortunately, the eruption stopped before it got out on Nátthagi, because if it would have gone out on Nátthagi, then it would have gone over the South Coast Road, which then would have cut off the access to the western part of the Reykjanes Peninsula. Now, all of these eruptions that we've been talking about, on the grand scheme of things, they're actually very, very small. So this is the real size of those lava flow fields for, not all of them, but 6 of them, compared to the Holuhraun lava flow field from 2014-15. Which was a medium-sized eruption. Not a very big one. But you can see these are even smaller. But there's an important lesson in there, because if you think about the hazards that this one has done, which is basically 0, didn't create any threat at all, compared to what these have done. We have created all kinds of threats. They have threatened a lot of infrastructure, both roads. They took the hot water off for a period of time in the Reykjanes Peninsula, and that's a very important thing in Iceland because we use our hot water to heat up our houses. So that basically the heating elements were gone from about a community of 35,000 people. It took, threatened the power plant. If that would have gone out, then electricity is gone as well. And if it would have taken out the roads completely to Keflavík Airport, so Keflavík Airport is right over there. This is the road to Reykjavik. The South Coast Road is down here. And if it would have taken out those 2 roads, then this is completely isolated, and that would have affected all of Iceland, because that means that tourism is non-existent for that period of time when these roads are closed. And 40% of our economy is tourism. So, and a little bit about, before I get into the hazards and finish this up, I want to just mention a little bit about magma storage. So recent studies that we undertaken, we did some seismic tomography. We found out that sort of between 9 and 12 kilometers, we have actually a fairly large magma storage, which may contain as much as 25 cubic kilometers of magma. And this was emplaced sometime between 2015 and 2020. And this here is probably the reason why we started to have this unrest in the Reykjanes Peninsula, the formation of this deeper storage zone. and it's also maintaining the activity. Now, under the Svartsengi, some of you may have heard about this, and I haven't really talked much about it, but what we see, I've noticed that Svartsengi is that we have land inflating, so the land is rising. And we can measure this fairly easily. And that is because magma is, especially in 23, magma started to flow from this deeper reservoir into a shallower storage zone at about 5 to 6 kilometers depth. And as you were filling that in, you had to make space, so you lifted the surface above that area. And then we had eruptions when you actually built up enough pressure or tension in here that you could rupture the roof. And the lava just flowed that freely to the surface, you had an eruption. But as doing that, you emptied this shallow magma storage zone. So it deflated down again. And then you started the process again, filling it in, inflating, rupturing the roof, eruption, deflating, and so forth. And that explains all these eruptions that we had. And so that these 6 eruptions that we've had on Sundhnúkur are because we are filling and draining that shallow magma storage zone. I want to talk a little bit about the last one, when the activity, like I told you earlier, the activity in the first eruptions usually is propagated to the south. In this one, it propagated to the north. But this eruption started exactly at the same location as previous ones. And it started propagating to the south, but then about an hour into the eruption, we started to see some propagation to the north, and there was a sudden change associated with a big earthquake that took place roughly an hour into the eruption, about magnitude 4.5. And that actually caused the activity to shift much further north and to the vents that were north of the water divide in the peninsula. So basically what the importance there is that any lava produced by these new vents that were north of the water divide, they would go to the north and towards the Reykjanes, the highway to the airport, or the airport road. Let's just call it the airport road. And we don't know exactly why and how that happened. And there are 2 possible scenarios, I think, is that you basically, the conduit that was active early on in the eruption, you just turned it off and you formed a new one. And this big earthquake actually opened up a new pathway from the deeper magma storage zone. But there's also a possibility that you also lengthen that shallow magma storage and you close to just the upper half of the conduit and you formed a new one that led to the northern one. So that is sort of at least the view that we have in terms of that. Now, like I said, you fill the shallow magma storage to the point of failure of the roof, and you get eruption, and you have the land just basically drops down because you're draining that magma storage. So it's like a balloon, you filled it up with air, and then you took the air out. You filled it up with air, and basically that's what these things are showing you. Take a notice that these are measurements. These are actually actual measurements in terms of height of this particular station, which happens to be Svartsengi. That's where the Blue Lagoon is and the geothermal power plant is. These things, number one, they don't go all the way down. So you've added in material here, but you're not taking all of it out. Possibly. If you've taken all of it out, then you have to have something else that actually lifted the land up to actually end up here. And the net effect is that the land has been rising. And if you take, these are millimeters, so that's about 800 millimeters. So it's about 0.8 meters that the land is higher now in this area than it was before this whole thing started. So there's a possibility that either you fill this up, you take part of what I was in there and erupt it, and you leave the rest in there, and then you start the process again. You put in the same amount of material as you did before, or you totally emptied it. But maybe the deeper reservoir is also inflating, and that's causing a background inflation. So it is, and that is what is lifting the land, these additional 80 centimeters or so. Very quickly here, this is estimated volume of magma that has been added to this shallow magma storage pre-Thor eruption. Very similar pattern. You get up to a certain volume, you create a situation where you have rupture of the roof, and you take out the magma volume, and then you start the process again. You get this sort of a sawtooth kind of like pattern. And you can see this is the status right now. And if you look at here, you see that this is not rising anymore. It is also an interesting thing. But this has not quite reached that level that it had before the last eruption. So we still got a couple of weeks to go before we have eruption. So by the time I get home, it will erupt. And very quickly, I think I'm out of time, but very quickly, just a bit about hazards in this area. When you're thinking about hazard, you need to know a number of things. And the hazards, what are the hazards? They're tetrafall. You can actually have explosive eruption producing some ashfall or tetrafall. You have gas coming out of these vents, and that you can have severe gas pollution that may affect communities. And lava flows. We have effuse eruption and lava flows. But another thing that is actually quite important is the location of the eruption sites. Where are you going to have an eruption? Where is the most likely places you have an eruption? And this is what we call eruption susceptibility. This is basically using all the geological data that we have access to in terms of volcanic activity on the Reykjanes Peninsula, and using that to actually calculate out where are the most likely eruption sites going to be in the future. And we did this in 2018. So we've had this information then, and so basically the brighter the color is, the more likely you're going to have eruption in that area. And this is actually not only important for thinking of volcanic eruption, but it's also important for planning. And if you're thinking about putting infrastructures in or even build up communities, you don't want to build it here, you want to build it there. That'd be your preference, really. So it's quite a useful thing. And these are things that are at stake. And so, of course, people, the threat to communities, threat to infrastructure, it also can influence the market, the economy, and tourism. So we have to think about how are we going to deal with all this stuff. And, I think we skipped something. Oh, I must have deleted that. Oh, here it goes. So, when we're thinking about hazards, we need to think about the location, the event intensity, magnitude, and length. And when you take these things together, you can have a small eruption that can actually have bigger impact than a big eruption because it just happens to be very close to important infrastructure or communities. And of course, there's also the human element in this. It matters how we respond to these things and how well we understand them and know them. Do we know really how to actually deal with these events when they happen? So that information is quite important as well. And so how am I doing on time? Over.
You're out of time.
Yes.
All right, it's 6 o'clock now.
Oh boy. I knew something like that will happen. So anyway, you need to know where the lavas are going. And also need to understand how you can prepare yourself for these things. Oh, sorry. And if you can do any mitigation, these light colored lines are all the berms that we raised around these important infrastructure, the Blue Lagoon, the geothermal power plant, and the town of Grindavik. And these are lava flow simulations. This is not real lava, which we use in trying to assess how these things will happen. And we, just to end this up, is you can simulate a lot of things with good models, but this is a lava flow simulation. It's looking at number of eruptions coming from different vent systems that we think could potentially erupt in this area. And this would be the outcome if we did nothing. We just let the lava flows freely and don't even in. This is the outcome if we put in protective walls and try to divert the flow of lava. And this was done before these events really started as an assessment. And it actually, interesting enough, it's more or less actually what we've seen is what was predicted. So we're doing pretty good. And with that, I'm just going to stop. Sorry for keeping you
Sorry
so long.
to cut you off there. We do have some time for questions. Does anyone have any questions for Thor? All right. I'll come over.
Okay, so on the topic of mitigation for the lava flows, I'm just curious what the berms are made out of.
They're made out of local material, basically just the ground, the earth around, more or less. And then when we need material, additional material, that basically is just taken from quarries around and driven in. So there's nothing magical about the material, which basically, and the reason we do that is because we did experiment in the 21 eruption, where we actually raised berms made out of this basically on-site material, and we wanted to see if it would work. So we actually placed it right in front of the lava flow. And the lava flow came towards it, and it actually stopped the lava flow some time until it had jacked it up enough so it could flow over it. But the berms actually did the job. And so we don't need any fancy material. We can just use whatever is there.
That's nice.
Yeah.
So you said the sinking of the land was due to like the deflation of magma chambers. Is there like a possibility of like a slip strike fault in the area, or is it just deflation from magma chambers?
No, to be perfectly honest, and I probably should make it, both things happen. So the main subsidence, if you like and I formed the subsidence structure or the grabens in Grindavik, that's all tectonic. And so you have both normal faults, and interesting enough, there's a fair bit of strike slip faults as well. So you have combination or dip slips and transtensional kind of movements. So you have extension actually on fault that is primarily moving laterally. And so you have both. But the magma inflation, deflation is very localized. And it's centered on Svartsengi or the power plant. And it only sort of extends about 2 kilometers away from that area. So it's pretty localized up and down there. But the plate boundary movements, which are still ongoing, they are affecting a much larger area and are also an order of magnitude greater in terms of vertical movements.
So this is more of a chemistry-related question. You mentioned there's gas pollution. I don't even know what comes out of volcanoes, probably sulfur dioxide, water. I don't know. What are the implications, I mean, around the area for people are hanging out and parking their cars right next to it. I mean, what are the implications of the air pollution?
The number of things that can, in these eruptions, the pollution is reasonably confined, and it's most intense right around the eruption site. But it's very, how do I put this? The gases you get coming out and are a danger to us is carbon dioxide, it's sulfur dioxide, it's chlorine, it's fluorine. Those are the kind of the worst. And of those, sulfur is usually the component that has the most widespread impact in terms of pollution. Carbon dioxide can actually, because it's heavy on the atmosphere, it will sink and sit in the lows. And if you happen to walk into that low, you're never walking out of it again. That's as simple as that. Fluorine is nasty when you get it in overdoses. And that affects, for example, we know this from past eruptions in Iceland, it can affect the grazing livestock. So you get fluorosis in those and softening of bones and bone tissues. And that people think even that happened to humans, which were both breathing and also consuming those animals that actually were affected by the fluorine poisoning. So when you're close to an eruption, that you really need to be aware of what the dangers are. You should have, everyone is there should have gas masks. And that's at least all of the scientists who go in, they have to have gas masks. And simple rule, stay upwind. Don't be downwind of the vents. Now, we also should remember that gases from volcanoes are also the ones that maintain our atmosphere. The reason why we have atmosphere still today is because of volcanic eruptions.
So giving the potential for wiping out the roads, the important roads, are they doing anything to sort of think about alternatives?
We are thinking about it a lot, and depending on, well, everyone is hoping that it will stop before something happens. That's the preferable solution that the politicians see. It's like, can't you make this stop? And it's also, it's hard to sort of make a decision on should we go into some kind of a long-term solution when we don't know how long this is going to last. So people are weighing options, trying to figure out what we can do, and taking the decisions that are economically viable as well. So I just happen to be in that infrastructure group that actually has to make those decisions.
These have all been really good questions, but I have a question that everyone's kind of wondering but doesn't want to ask. How does having a name like Thor, how do you deal with unrealistic expectations of yourself that Americans have?
I don't. That's a simple answer. I'm sorry to disappoint you all.
Right. I think we have time for one more. Any other questions?
I'll ask. Well, the lava was flowing to the north.
Sir. Excuse me.
The lava was flowing to the north, and I don't remember any barriers being constructed. Is there plans for barriers for flows to the north?
Yes, and realizing that if we build barriers there, they will actually be perpendicular to the flow direction. And they will only be a temporary measure. If the eruption continues long enough, then it's you're going to have to let it go, just go over the road. Some of my colleagues said, like, well, that's not a problem. We've already built roads over newly formed lava flows, and they're still steaming, and the road is relatively hot and all that. And I once said, I'm not sure that busloads of tourists are going to be very happy by driving over still an active lava flow. So we have to come up with something. And there is no easy solution. The long-term solution in my view, for Iceland is to build another international airport in an area which does not have these kind of threats to it, like volcanic eruptions and. Well, it would be more either in around Selfoss in the south, on the flat lowlands there, or in eastern Iceland around Egilsstaðir. And that we really need to do that. We need to have 2 international airports that have roughly the same capacity, and they are also in different parts of the country, so they're not under the same threat.
All right. Thank you very much, Thor.
Thank you.
Appreciate it.
Thank you all
Thanks.
for coming.
Thank you, everyone, for coming.